Welcome to The Explainer. Today, we're tackling an architecture that is absolutely brilliant when it works perfectly, but a complete headache when it breaks in production. We are decoding the exact pipeline needed to make Retrieval-Augmented Generation, or RAG, reliable in the real world. We're moving way past those simple sanitized tutorials you see everywhere and looking at what it actually takes to build a robust, enterprise-grade system that engineers can truly trust. You know the feeling, right? It's a situation almost everyone in the AI engineering space runs into. You build a basic RAG demo over a weekend. You feed it a perfectly clean 10-page PDF, ask it a question, and boom, it gives you a flawless answer. You feel like a genius. But then you try to deploy that exact same architecture to your enterprise data. Suddenly, you're dealing with a messy, complex reality. We're talking about thousands of poorly formatted Confluence pages, outdated Jira tickets, inconsistent metadata, and raw code snippets. When standard RAG hits that environment, it becomes a literal nightmare of irrelevant results. The context window just gets flooded with noise. So why does that happen? Why do so many of these systems completely fail the moment they face real-world enterprise entropy? Okay, let's dive into this. Here's our roadmap for today. 1. The production RAG problem. 2. What is hybrid search? 3. The power of re-ranking. And 4. Building the ultimate pipeline. Starting off with Section 1, the production RAG problem, demos versus reality. Let's start with the diagnostic of why those naive AI wrappers we see online hide some serious pain points, and honestly, hit a massive brick wall in enterprise environments. In a basic setup, you take a user's question, turn it into a dense vector, and use cosine similarity to find the closest matching vectors in your database. But in reality, this often pulls up completely irrelevant context. And look, if you feed a large language model irrelevant information, it's going to do what it does best. Try to make sense of it anyway, which leads straight to hallucinations. Furthermore, basic semantic search is notoriously bad at finding exact term matches. It struggles heavily with out-of-vocabulary terms or specific alphanumeric codes. If you're looking for a precise product SKU or a super niche acronym, basic vector search might gloss right over it because it's mapping the proximity of meaning, not exact spelling. The end result is a deeply fragile system. Moving right along to Section 2, what is hybrid search? Marrying meaning and keywords. So how do we fix this? Well, this is our first piece of specific medicine for that basic pipeline. To really understand it, think of navigating a massive library. Keyword search, which relies on algorithms like BM25, creates sparse vectors based on term frequency. It's exactly like asking the librarian for a specific identifier. You want the book with ISBN 978-3-16-48410-0. It is highly precise, but it doesn't care at all about the underlying concept. Vector search, on the other hand, utilizes dense embeddings generated by a neural network to capture semantic proximity. It's like asking for books about space travel. It gets the vibe, the concept, even if those exact words aren't in the title. But by themselves, each approach has a critical blind spot. Vector search completely misses exact serial numbers, and keyword search completely misses conceptual synonyms. Hybrid search simply brings both of these incredible powers together into one single retrieval step. So the crucial point is, we simply cannot rely on semantic meaning alone in production. Just think about the consequences for a second. If a site reliability engineer searches your company's internal diagnostic bot for error code E404B, they need the specific runbook for that exact code. If the bot returns a conceptually similar manual for general network errors, that engineer loses trust in your tool immediately. We have to cast a wide, hybrid net using both dense vectors and sparse keywords to retrieve all the necessary data. However, grabbing both keyword matches and semantic matches means we've now retrieved way too many results. They're messy, and they're entirely out of order. Which brings us to Section 3, the power of re-ranking, sorting the chaos. We need a specialized solution to sort through that massive pile of documents we just retrieved, and that solution is a cross-encoder re-ranker. Going back to our library analogy, if hybrid search is the team of assistants who ran through the aisles frantically grabbing every book that might match, the re-ranker is the highly specialized head librarian. Technically speaking, initial retrieval uses biencoders because, well, they're fast. But a cross-encoder evaluates the user's original query and the retrieved document together, passing them simultaneously through a transformer network. It's pretty computationally heavy, which is exactly why we only apply it to this final narrowed-down subset of documents. It meticulously scores the exact relationship, filtering the chaos and ordering everything perfect from best to worst before handing it off to the generation model. And this brilliantly illustrates the night and day difference these upgrades make. A basic vector setup yields low retrieval accuracy and, honestly, poor relevancy scores. But when you upgrade to hybrid search plus re-ranking, your accuracy becomes high and your relevancy scores jump to excellent. Take a metric like NDCG, or normalized discounted cumulative gain. In this context, a high NDCG means the absolute best, most highly relevant answer is shoved right up to position number 1. This is critical, guys, because it prevents the large language model from getting distracted by middle-tier context. By dramatically filtering out the noise, we drastically improve the quality of the text the LLM actually consumes. The result, a hallucination-free answer. Let's wrap it up with Section 4, building the ultimate pipeline, putting it all together. Let's move to and see how this builds a completely bulletproof system. Step 1, the user query comes in. Step 2, we use hybrid retrieval to cast our broad net. In practice, this often happens in parallel. We're making asynchronous calls to a vector database for conceptual matches and a keyword search engine for exact terminology at the same time. Step 3, we take that large, combined payload and pass it through our cross-encoder re-ranker. This acts as the absolute critical bottleneck filter, bubbling the most relevant context right to the top. And finally, step 4, we take only those top, perfectly relevant results and feed them into the LLM. Because LLM token generation is expensive and the models are easily confused by long, rambling contexts, feeding it only the pristine data from step 3 pretty much guarantees an incredibly accurate answer. By combining the wide net of hybrid retrieval with the precise, computationally heavy sorting of a re-ranker, you are literally eliminating the noise that fundamentally breaks AI models. This specific architecture is how you move an AI tool from being a cool weekend toy to a dependable, secure, and highly accurate enterprise application. It's how you actually save a company time and money, ensuring no exact keywords are ever missed while completely curing those dreaded hallucinations. So I'll leave you with this final challenge. Take a really hard look under the hood of the AI applications you're building or currently deploying at your company. Are they secretly just relying on simple, basic vector search, or have you actually implemented the robust engineering of hybrid retrieval and cross-encoder re-ranking? Ultimately, is your RAG pipeline truly ready for the real world? Keep exploring, keep auditing that tech stack, and thank you so much for joining me for this explainer.